Thank you, Alex, for your kind introduction. And going back to the title of the talk, it's a pleasure and an honor to be here sharing with you some of the work that we have done in the Catalysis program using state-of-the-art facilities that we have in the chemistry department at the synchrotron light source and at the Center for Functional Nanomaterials. So it is possible that many of you have confronted catalysis for the first time when you had to change the catalytic converter and you realize that it's more expensive than your 10-year-old car. And in here, this converter is used to mitigate the emissions of your combustion engine. Now, in the car, also every single drop of gasoline that you use has gone through extensive catalytic processes to remove contaminants from oil, such as sulfur, and also to increase, for example, the octane of gasoline. The energy that you put in your body, the food, is also somehow a product of a catalysis that is related to the synthesis of fertilizers. In fact, 90% of all industrial chemical processes are catalytic. So catalysis really is present with us in every single aspect of our life. During this presentation, I'm going to give a brief introduction to catalysis. I will then describe how we use state-of-the-art facilities here, where we use light, whose fundamental particles are photons, and electrons, which are charged particles, to study these catalytic processes in situ. And I will present a case study of an industrially relevant catalytic reaction that is used for the production of clean hydrogen that is called the water-gas shift reaction. This is a reaction that the Catalysis program has been investigating for more than a decade. With what we have learned during these investigations at the fundamental level, we have recently introduced a new kind of active sites on catalysts that we have prepared that are able to hydrogenate carbon dioxide to methanol more efficiently than the industrial catalysts that are present today. So let's start with just the fundamentals. What is catalysis? Here we have a seemingly simple reaction. We have carbon monoxide, and we want to oxidize it with molecular oxygen to carbon dioxide. In fact, this is one of the main reactions that happen in the catalytic converter. If we just want to do this in the gas phase, we would have to break these bonds in the oxygen molecule and somehow link those oxygen atoms to the carbon monoxide to make the products. Now, this is a process that is not easy. The oxygen is a very stable molecule, thankfully, because that's why it's present in the atmosphere and we exist. And then, if we want to do this just by brute force, by heating, we would have to go to fairly high temperatures to overcome what is called the activation barrier to make this process happen. In fact, we would have to heat the pipes of the exhaust near to 1,000 degrees. That's not very efficient and potentially very dangerous. So chemists have found other ways to do this in a more efficient way by introducing another component in the reaction, a catalyst, which in this case is a solid, and then these gas phase molecules can get together in the catalyst. Reactions happen there more easily. We can break bonds, such as the bonds of the oxygen molecule, get the molecules to diffuse, react, make products, and leave the catalyst free to start the process all over again, completing the catalytic cycle. The energy required for this alternative pathway with the catalyst is related to the energy of the most difficult step, in this case, the dissociation of oxygen, which overall is significantly lower than the energy required to do the process between the gas phase molecules without the catalyst. Since the introduction of the concept of catalysis by a Swedish chemist Berzelius in the 1800s, catalysis has played a vital role in the chemical research. These are just a few of the scientists recognized by the pioneer work in the field. I would like to highlight the work of Paul Sabatier in hydrogenation, who was one of the first scientists recognized in the field with a Nobel Prize. And one of his legacies is what is now known as the Sabatier principle. What this principle tells us is that we can increase the rate of a chemical reaction by increasing the interaction, the heat that can be measured as the heat of absorption of the molecules with the catalyst. Now, we reach a point where if this interaction is too strong, we cannot release any longer the products and establish the catalytic cycle. Therefore, what this principle establishes is that we need to find a balance between a strong interaction so reactants can get together, but not so strong that we cannot remove the products. The next example that I want to highlight is the work by Fritz Haber in the synthesis of ammonia. This is, again, a hydrogenation reaction, in this case of nitrogen present on the atmosphere with an iron catalyst to make ammonia. The ammonia is later used to make fertilizers that have enabled to produce food at the growing rate to be able to feed the growing global population. It can be argued that this is the single most important scientific discovery in the history. One of the latest recognitions in the field was given to Gerhard Ertel for his pioneer work on molecular studies of catalysis. We can see that since the initial definition of catalysis by Berzelius in the 1800s, the field advanced slowly. And only with the introduction of the ammonia synthesis, it started to play an important role in industrial processes. Still, all along, this was primarily the progress came through trial and error. Only when we started to understand the fundamental processes in the work pioneered by Ertel and others in what is called now the surface science, we were able to translate to a higher rate of advance in technological industrial catalysis. So now that we have some fairly good idea about what a catalyst is, we are going to discuss how we can develop techniques to study these processes in situ. Why do we need to do this in situ? The Department of Energy has recognized as one of the grand challenges for research in basic energy science the understanding of mechanisms and dynamics of catalyzed reactions. Now, to be able to do this, we have to recognize that even though the catalyst doesn't form part of the products, when it interacts with reactants, it gets modified. So we can only get to understand at the molecular level the reaction mechanisms if we follow these processes in situ. This is how it looks in industrial complexes where hydrogen is produced. It's a marvel of engineering which can be as big as a small city. The catalysts that are used in the reactors in this complex are also materials extremely complex. In fact, one catalyst can have about half of the periodic table of elements for different purposes and properties required for the processes. At the end of the day, the magic that enables all this to happen occurs here at the nanometer level where the molecules interact with the surface of catalysts. Now, due to the high complexity of these systems, it's impossible to try to understand these processes at the molecular level with these systems. And that's where the surface science approach comes into play. In here, what we do is take out one of the most reactive components of the catalyst that in most cases is a very reactive transition metal such as copper, and then we put this in ultra high vacuum conditions. That means pressures that are close to the outer space. That allows us to prepare very clean atomically flat surfaces. If we would have this metal here on the room, it would be contaminated in less than microseconds, and we could not study the interaction with a particular molecule, such as carbon monoxide. Now, we also want to increase the complexity of the materials that we study to incorporate more elements present on the industrial catalyst. The next important one is to study oxides of reactive metals, such as cerium. In this case, when we are oxygen, we can have many different phases for the same stoichiometry, the same composition of elements, but we can nowadays study this in quite close detail at the atomic level. And we can, even now, have the two components, the metal and the oxide, present in the same model. So we have improved significantly the complexity of the model system that we can study with molecular resolution. But still, if we do these studies in ultra-high vacuum conditions, we can only study the initial process of catalysis. That means the absorption on the catalyst and the reaction, the dissociation of those molecules. If we want to establish a catalytic cycle, the only way that we can do that is by increasing the pressure at which we do our studies, going closer to 1 atmosphere or above, at which pressures occurs the industrial catalysis. Now, we need to go only as far as we start to see catalytic reactions happening, and the challenge in this direction is really the development of techniques that allow us to follow these processes in real time, that means in situ, while they are happening. The arsenal of techniques that have been developed for ultra-high vacuum conditions cannot be directly extrapolated to study these processes in situ. By doing this approach of increasing the complexity and developing of the materials and developing in situ techniques, we can slowly start to make a bridge from this region where we know exactly all the players in the game, how they interact, and start to go to more crowded places in more complex environments where we can still follow the reactions before we get to these hectic places where we never know all the players, things happen, but we don't know why. So by doing this approach, we are building up our knowledge towards understanding catalysis. These are the techniques that we have here in the lab. The first one is infrared reflection absorption spectroscopy. In this case, we use live photons in the infrared region, which interact with vibration of molecules both in the gas phase and molecules absorbed on the surface of the model catalyst that we have prepared. The challenge here is to devise instrumentation and approaches that allow us to differentiate between molecules that are reactants or products from those that are at the surface of the catalyst. We also use light in the X-ray region that we obtain from the synchrotron light source that interacts with both molecules and atoms on the catalyst. And then, if we look at the electrons emitted during that interaction, because we excite core-level electrons from these molecules, we can get the chemical state of both the molecules and the atoms, and we can be very sensitive to just the very top layer of the catalyst, to the surface atoms. And we use scanning tunneling microscopy with electrons to follow changes in the morphology of the catalyst as the reaction progresses. All these techniques we can nowadays here in the lab use them up to pressures of about 10 torrs, where we find that several of relevant catalytic reactions are starting to work. So I will start focusing on scanning tunneling microscopy. In this case, the challenge is that when we go to these pressures, we have to apply here high voltages to drive the components that are needed to move these scanners. And then we can have plasma discharges. So that had to be resolved to be able to use this technique. And the other challenge is that these electrons interact very strongly with molecules in the gas phase. Therefore, we have to either increase the current, the number of electrons, but that has the potential problem that we can start damaging, altering the composition of the surface, or we have to increase the sensitivity of our system. We have installed a state-of-the-art ambient pressure scanning tunneling microscope in our labs in the chemistry department 2 years ago, and I'm going to show you the results of the first set of experiments that we have carried. In this case, we were looking at the reaction on a copper oxide surface. This copper oxide surface is composed of hexagons of alternated copper and oxygen atoms, and this is a reducible oxide. That means we can remove oxygen atoms from the surface by interacting with a molecule such as carbon monoxide. By doing this at moderate pressures of about 10 millitorr at room temperature, we can fully reduce the oxide to a metallic surface. These are single copper atoms that we see at the end of the reaction. We can follow this process in situ with our ambient pressure STN microscope, and in this case this is a bigger image, that's why we don't have atomic resolution of the atoms, but we can see here 3 terraces where all at the starting point are oxide surfaces. As we introduce the carbon monoxide, we see that we start to make fronts of metallic copper, primarily from the steps between 2 terraces, but also in the middle of the terraces. If we stop here, we can see that in between the metal islands and the oxide terraces, there is a region that has a different contrast, and we will get to it later. But if we continue the reaction to completion, we can see that at the end of the reduction of the oxide, we end with a surface that is fully metallic, and the morphology has been completely altered from the initial surface that we had to start the reaction. Going back to this region of between the metal and the oxide interface, if we zoom here, what we found is that we have a partially reduced oxide phase where that it has not only 6-member rings, but also rings with 5 and 7 members. And when this phase appears on the reaction accelerates significantly. So this phase, which we would not be able to know that existed were we to look only at the starting point or the final point of the reaction, is actually much more reactive than the original oxide. We can further zoom in and look at, with atomic resolution, the initial steps of the reduction of the copper oxide surface. When we start, all the atoms in the copper oxide are copper plus cations. As CO starts to remove oxygen from the oxide, metallic copper atoms are released from the oxide, and interacting with carbon monoxide, we see that they rapidly diffuse to make a small metallic copper nanoparticles which sit on top of the partially reduced 5, 6, 7 members phase. And this is, in fact, the phase that is the most active for this particular reaction. Now that we have seen how we can use these in situ techniques to look at catalytic reactions in situ, I'm going to show the case study of our research on the water gas shift reaction for the production of hydrogen. Now, hydrogen was proposed in the mid-70s as one possibility to replace our economy based on fossil fuels. We have made tremendous advances in this field, but still we are far away from this ideal world where we only use hydrogen. Even though we haven't reached that stage where we have replaced all the fossil fuels with hydrogen, we still need plenty of hydrogen around. On a yearly basis, hundreds of millions of tons of hydrogen are produced for use in the chemical industry. Very little goes to the few hydrogen fuel cell cars that are driving across our roads. Half of it goes, in fact, to the synthesis of ammonia. About more than 2% of the global energy consumption is devoted to this process. About the other half goes to the treatment of fuel for the generation of the gasoline that we use in our cars. We have recently introduced a new line of research where we are trying to look at ways that we can use this hydrogen to convert captured carbon dioxide into an alternative fuel that could be an alcohol. Now, in the ideal world, we would like to produce this hydrogen from renewable sources, and there is significant research in this direction, including in our chemistry department with splitting of water. But the case is that more than 95% of the hydrogen that is produced today and in the foreseeable future comes from fossil sources. Today, most of it comes from natural gas, but that has been changing depending how things move. It can come from oil, coal, or biomass. All of these fossil sources can be converted in hydrogen by reaction with water or oxygen, but this hydrogen stream that is produced has a high content of carbon monoxide. Carbon monoxide is not only poisonous for us humans, but also for the catalysts that are used downstream in the chemical industry. Therefore, we have to find a way to remove this carbon monoxide, and the main process for that is the water gas shift reaction that oxidizes carbon monoxide to carbon dioxide, but also produce extra hydrogen. The industrial catalyst used for this process is a catalyst based on copper, sitting on zinc oxide. In the catalysis program, it was reported in 2007 in the group led by Jose Rodriguez before I joined Brookhaven, that a gold catalyst, which is completely inert for the water gas shift reaction, could be activated to behave similar to copper metal if we deposit oxide nanoparticles of reducible oxides. And it was shown theoretically that for the case of titanium, it was critical the presence of sites that combine the oxide and the metal. One of the goals when I joined the program was to try to use these new in situ techniques to see if we could experimentally investigate this process. For that, what we did was to prepare a series of copper-based catalysts and use a copper nanoparticles on zinc oxide as a reference, which is the model for the industrial catalyst for the different catalysts that we produce. Here we are plotting 1 over the temperature, so this is lower temperatures and higher temperatures, and here we see the production of hydrogen. This is called an Arrhenius plot, and we can directly obtain the activation energies for these catalytic processes. And it's important to notice that this is a logarithmic scale. Therefore, a change in unity here means an improvement of 1 order of magnitude in the production of hydrogen for this catalyst. If we just plain copper, it has a lower efficiency than our reference catalyst. If we now introduce one of the reducible oxides that were shown as nanoparticles to be active, it actually has 0 activity for this reaction. But if we deposit a nanoparticle of copper on top of this reducible oxide, we now obtain a more active catalyst than our reference model catalyst. And if we use the inverse configuration, where we now have nanoparticles of the reducible oxide sitting on top of metallic copper, we obtain our best catalyst. So we decided to try to look at this process with our in situ techniques, at this catalyst, to see if we could determine what is the reaction mechanism. The reaction mechanisms proposed for the water gas shift can be described mainly in these 2 processes. There is a redox mechanism where water is dissociated into OH or hydroxyl groups. Then these ones are further dissociated where hydrogen then makes molecular hydrogen and goes to the products, and the oxygen left on the surface is the one that oxidizes carbon monoxide. The other process is the associative mechanism, where carbon monoxide, in this case, reacts with the hydroxyl groups coming from the dissociation of water. It creating these surface intermediates that later on go into producing carbon dioxide. The 2 main surface species that had been proposed to be relevant from experimental studies were carbonates and formate species. But experimental studies found that there could be a more efficient reaction mechanism through another species, a carboxyl species, that is the same as the formate, but with a different bonding to the surface. Instead of having 2 bonds, it has only 1 bond. but there was not experimental evidence that this reaction pathway could actually happen in a catalyst. So to study this catalyst and try to shed some light into the reaction mechanism, we first use ambient pressure XPS. In this case, we shine with X-rays our sample, but then we are also exciting molecules in the gas phase because we are under reaction conditions. And then we emit electrons both from the sample and the gas phase that have to travel across these molecules. They interact very strongly, and under pressures that are used to establish a catalytic reaction of about 1 torr, the mean free path is below 1 millimeter. Then we need to introduce here a small hole, get the sample very close to the entrance to the analyzer where we are going to detect the electrons, and differentially pump molecules to allow this electron to travel longer all the way to the detectors. We need several of those differential pumping stations, and that decreases the number of electrons that would make it, so we introduce electrostatic lenses. And all this technological development has allowed us now to use these techniques to look catalytic reactions in situ. When we started our studies, we took our model system to Berkeley to do experiment at the advanced light source, and we measured the oxidation state of our cerium nanoparticles when we started the process. They were close to fully oxidized. The cerium took as much oxygen as it could. But as soon as we put carbon monoxide and water to enough pressure and temperature to be able to produce catalytically hydrogen, what we observe is that the cerium nanoparticles got almost completely reduced. And this is the first very important piece of information, because if we now want to do any simulation and build a model of a system to explain this reaction, we have to take into account that the active phase of the cerium nanoparticles are heavily reduced cerium. We can also look at the surface species present under reaction conditions by looking at the carbon 1s spectrum. We started with just plain copper, and under those conditions we see the presence of CO in the gas phase, some carbon on the surface, and the only surface species present on top of the bare copper metal was carbon monoxide. This is consistent with a redox process happening right here on just the plain metal. If we add the oxide nanoparticles, we have very clear evidence that we produce surface intermediate species that correlate with an associative mechanism. But we cannot determine which one of these different alternatives were present in this case. For that, we use complementary infrared ambient pressure spectroscopy, and we were to determine unequivocally that the species present under reaction condition is an activated carbon dioxide molecule. Now, using the principles of this technique, we know that we can see only modes that have a perpendicular component to the surface, because there is an image dipole moment that adds to that component. If it is parallel, actually it cancels out. So in the case of this carbon dioxide molecule, it has two main vibrational modes. One is the symmetric, and that has a component perpendicular to the surface, and we clearly see. But the other mode is asymmetric, and therefore, based on this surface selection rule, we should not be able to see, but we do see that mode. What this is telling us is that the molecule cannot be sitting in this condition, and then we know that it's sitting right at the interface between the metal and the oxide nanoparticle. So this is great. Case closed. We know what is the surface species, and we know where it's sitting. The only problem is that this surface species was nowhere to be found in any of the proposed reaction mechanisms. So we have to go back to our friends and that do the calculations and tell them what we have learned with our in situ studies, that we need a model using heavily reduced cerium nanoparticles sitting on copper. In this case, water can very easily dissociate on the reduced oxide nanoparticles. Carbon monoxide can sit on the metal, and now these two molecules, the carbon monoxide and the hydroxyl groups, can react to make the elusive carboxyl intermediate. this can very easily dissociate back or go all the way to the products. And when it goes to the products, it can actually, under certain circumstances, be stabilized as a carbon dioxide molecule right at the interface. And this is what we actually find experimentally. So by combining these in situ experiments with theoretical calculations, we were able to demonstrate for the water gaseous reaction that on top of the metal, the dominant process is a redox process, but when we include an oxide right at the interface, we activate a much more efficient associative mechanism for this reaction. And in fact, we repeated these experiments with Syrian nanoparticles sitting in gold. That was what was reported in 2007 in the group, and we found the same to hold true. Now, we learned that we are activating this carbon dioxide right at the interface, and that led us to think if we could use this catalyst to now transform this carbon dioxide by hydrogenation into methanol. This is driven in part by what George Olah has been promoting since the mid-2000s, that there could be a methanol economy to replace our dependence on oil and gas, rather than the hydrogen economy, and that this methanol could be derived by the hydrogenation of captured carbon dioxide. In fact, in 2011, an industrial complex in Iceland, Carbon Recycling International, had started production of methanol based on captured CO2 for geothermal sources using a copper zinc oxide catalyst. Recent reports have shown that for this particular catalyst, the most important active sites are alloys between the copper and zinc from the oxide support. And based on these results, there has been research trying to find better alloys that would fulfill the Sabatier principle of optimizing the interaction with the reactant molecules. Now, during this research reported last year, it was found that the copper zinc alloy from this catalyst sit very close to the top of the curve. So really going in this direction, trying to optimize catalysts by making alloys, doesn't seem to hold much promise. But if we now try to find a different kind of active site, such as the one that we found of metals and oxide, we could have a chance. So we used the family of copper-based catalysts that were active for the water gas shift to look at the reactivity for the methanol synthesis, and we see that in fact the nanoparticles of Syria sitting on copper are more active than the model catalyst representing the industrial catalyst. And that if we now produce a catalyst where we have both components, the oxide and the metal, as nanoparticles, we obtain a catalyst that is more than 2 orders of magnitude better than the industrial catalyst. To understand why, we go to the more simple nanoparticles of oxide on top of the copper system, and as we start, we have to oxidize the nanoparticles, and by doing that, we oxidize all the substrate, the copper metal, but when we expose it to the reactant hydrogen in this reaction, we see that all the copper, it goes as copper metal, it becomes metallic copper, the Syria gets heavily reduced, but not only that, the defects of oxygen that are creating nucleate, making big holes on the nanoparticles, are increasing the perimeter of these critical Syria-copper interfaces. We now can go and try to look at the reaction mechanism, and this is what we have to find. We start from carbon dioxide and hydrogen, end up with methanol and water, and this is the entire reaction mechanism. Now we could spend the next hour going through it, but we don't need to do that. The most important step in the entire process is actually the activation of this carbon dioxide absorption on the surface. If we have just carbon dioxide and want to absorb it with metallic copper, it's too weak. It doesn't absorb. If we have just the oxide, it's too strong. We are in the other side of the Sabatier plot, and it makes carbonates that cannot further be reacted. If we have the interface, we can actually absorb it based on theoretical calculations, and we can experimentally prove that that is the case. After we have activated the carbon dioxide here, we can now go through the reverse water gas shift and with hydrogen make carbon monoxide, which can now dissolve to the gas phase, which we see experimentally, or it can be hydrogenated sequentially all the way to produce methanol. So what here I have tried to show during this presentation is that we have established an integrated approach for the study of catalysis, where we prepare atomically resolved model catalysts and study their activity, the reaction kinetics. And the most promising catalysts then we can follow in situ with complementary techniques to determine what is the active phase of the catalyst, what surface species are present during the reaction, and use that input to prepare models to try to discern about the reaction mechanism that's occurring. This takes us closer to the grand challenges proposed by the Department of Energy for the 21st century, and also allow us to start to propose ideas for the rational design of better catalysts, such as looking at combinations of copper with reducible oxides that would create interfaces that would give a much better efficient catalyst for the hydrogenation of carbon dioxide to methanol. This now, in the future, we always want more photons and electrons, and we are happy that we will be able now to study not only planar catalysts but powders in the Center for Functional Nanomaterials using the environmental transmission electron microscope, and at the light source we will be able to push the limits, for example, for ambient pressure XPS and X-ray absorption spectroscopy from today's state of the art, where we can look at reactions at Tor levels all the way to atmospheric pressures, which directly correlates with the conditions that are used in industrial catalysis. I would like to acknowledge the Catalysis group. This is truly a collaborative research, and the group is led by Jose Rodriguez, and my collaborators are Ping Liu and Sanjaya Senanayake, and there are a number of postdocs and students that are the actual people that does the job. We collaborate internally with a group of Mike White and Jin-Wan Cheng in the chemistry department, and Aníbal Bosco-Voynick at the Center for Functional Nanomaterial, and we have several international collaborators that we benefit from a very fruitful collaboration. All the funding for this research came from the Department of Energy, Basic Energy Science, and I thank you for your attention. Yes.
About 15 years ago, fuel cell group at Los Alamos came up with the idea of getting rid of carbon monoxide by combining maybe 2% oxygen with the hydrogen. I was wondering if this was, I don't know how it works, but I was wondering if it would work something like that.
So the question is another way that you could remove the carbon monoxide from the stream of hydrogen. And the answer is, so yes, there are other processes, not only the water gas shift. It is preferential, that would be PROX, preferential oxidation of carbon monoxide with oxygen. So there are other ways that this could be done, and in fact, it is done in that whole scheme that I was showing for the purification of hydrogen. So, we haven't tested that. The fact is that Syria is using the catalytic converters, and that's a nasty environment. So I would say yes, it has been tested for the water gas shift reaction, and yes, it is good in powder catalyst. And we have been approached, Jose has been approached by people that is trying to do this for the hydrogenation reaction. The answer is we don't know. if it would be stable. But in principle, it's very hard to reduce Syria beyond Cerium 3+. So my guess would be that it should be stable.
Yes. Also, many years ago, before we had those probing instruments to look in situ what is happening in catalysis, we're postulating different reaction schemes. We're using, for example, action tracing, and we're looking then to verify our hypothesis with regarding of what were the products. Are you thinking of using perhaps action tracing in parallel to this type of studies?
So the question is isotope tracing?
Right, using, for example, for carbon monoxide, carbon-14.
Yeah, definitely those are different approaches that can be used that could give us ideas even for the reaction mechanisms. And we haven't done it, but it's a valid approach. In our case, the isotope labeling of reactants is particularly interesting when we use infrared spectroscopy. We could, because that can help us to determine what do we have on the surface and the products that we found, where do they come. We could actually isotope label the surface and see if the reaction requires oxygen from the surface of just reaction between the compositions of the reactant molecules. So that is something that is useful. Yes.
So in several of your graphs, you showed what looked to be atomic structures of the catalysts. But it wasn't clear to me how you get that atomic structure. Is it from the atomic force microscopy? And if so, how does that yield some of the structures you look at? Maybe there's theoretical computations that go into these predictions, how the catalyst works.
So the answer, so the question is, how do we get the atomic structures? We use a scanning tunneling microscopy, no atomic force microscopy, and in some cases we get directly there the atomic structure. Now, the scanning tunneling microscopy doesn't tell you what element is that bright blob that you are looking at. So we can do complementary experiments to know how does it look, different surfaces or components, and then when we have a more complex system, we can identify, but also we inevitably at the end, we combine this with theoretical calculations to obtain our atomic structures. So I think that that's the best way to look at this system is combining theory with experiments. And it's fairly hard. You could get atomic structures just from theory. The question is, are they even possible? Do they exist? You can get images from experiments. The question is, how do you determine? So when you put the two together, most of the work that we do is really combining the strength of theory and experiments. Yes.
In some of your pictures of the surface, you showed copper regions growing. And what I wonder is if the reaction is right at that interface between the copper and surface and the substrate surface. Is that the most active region? Because these clusters seem to be growing out from those regions.
So the question is, in the movie where we saw these copper domains growing from the oxide when we start to reduce it, if where is actually the reaction happening? And the answer is, I would agree with that statement. It's right at the interface between the metal and the oxide. When we had this high resolution image where we could actually see atoms in the initial reduction of the oxide, we do see that the initial steps happen at defects, the initial reactions, but after that you generate these copper atoms that nucleate to small copper nanoparticles. So even before you get to these macro copper islands, you already have copper nanoparticles that are in close contact with the oxide, and right at the interface is likely the most reactive site for the reaction.
Yes, but that sort of says it's a consumable and not a catalyst.
in the case of the movie that I was showing, that's a stoichiometric reaction, was not catalytic. The question of the active side, that's the holy grail question in catalysis, is a tricky one. So the system is dynamic. So what we can do with our in situ techniques is to try to see the most abundant domains that we see, and then we try to simulate and see which sites are the most reactive. Now what this is telling you is that you may see that you have crystalline oxide and crystalline particles, but then under reaction conditions you can have these very little nanoparticles that are dynamically created, and in fact we have done the study of the oxidation, the catalytic CO oxidation. There, when we bring oxygen, the tip is not as happy, so we don't have such a nice pictures, but we do see the dynamic creation and disappearance of metallic nanoparticles. So this is a dynamic process. This challenges this static idea that we initially have, because that's how far that we could measure of this structure that is the active side. This is a dynamic structure that you have to bring the molecules into contact, and it's constantly changing. I don't know if... Yes?
Theoretical simulations for the rate return step, you actually get rate constants, compose activation energies, factors, and are they both interesting?
So, in the case of the methanol hydrogenation, the hydrogenation of carbon dioxide to methanol, we see that the rate limiting step, the activation energy matches the apparent activation energy that we do measure experimentally. So yes, it is relevant, it's in the order of 10 kilocalories per mole for that particular process. So the matching is not exact, but it's pretty close, and I think that yes, is relevant. Yes.
So most of the data that you showed was, or a lot of the data that you showed was core level spectrum. If you wanted to look at the changes at the valence band, what would be the relative, the important length scale to be able to resolve to see what's changing with the valence band as you have the reaction occurring?
You mean UV spectroscopy?
No,
that
looking at the valence band photo emission, for example, up near the fermi.
And when you say, I'm trying to understand the question, when you say the relevant scale, size or energy?
Length scale. What do you think the relative length scale would be in order for you to have useful information about the catalytic process?
So the XPS and infrared is macroscopic measurements. It's not microscopic. It's macro for all intents and purposes. The only one where we could actually solve sub-nanometers is with a scanning tunneling microscopy. So if I have a millimeter spot size, that would be relevant for our measurements. Okay.
Okay, if there are no more questions, then go ahead. We'd like you to join us with some refreshments afterwards. We'd like to thank Dario for a wonderful talk.
Thank you.